Okay, hello everyone. I'm going to get started. It's a busy talk, so hello everyone. Thanks for having me today. My name is James Answer, and I'm a principal technical artist at Sony's London studio, where I've worked for almost 9 years. The team I'm on is currently working on virtual reality for Sony's forthcoming PlayStation VR, and I'm going to give you an overview of how we developed our tools. I'm going to give you an overview of how we developed our tools and technology around it. So I'm going to give you the mandatory reminder to set your phones to silent and fill in your evaluation forms. So first I'm going to talk about the early work on our new engine that we started preparing for PlayStation 4 and VR. Next, I'll have a look at the experiences the studio has shown so far and how they've shaped our engine. We'll then have a look at the tech that we've developed over since last year. And finally, content optimization for VR. We don't have a lot of time and there's a lot to cover, but I'll see if I can fit in a couple of questions at the end. And otherwise, I'll be in the wrap-up room just over the way. So London Studio has a long history of working with peripherals. We pioneered camera-based gaming and augmented reality with iToy, iPet and Wonderbook, as well as working with microphones and companion apps on SingStar. So working on VR is a natural fit for us, as we're used to exploring new technologies and the possibilities they bring. We became one of the first developers working with Morpheus, which was a codename for PlayStation VR. And true to its name, Morpheus became the source of all my dreams and nightmares over the last 2 years. A dream because VR is incredibly cool to work with, and being able to inhabit the worlds you create is amazing. And a nightmare because there are a hell of a lot of challenges in being the first. So our remit as a first-party developer and being VR evangelists is to introduce and showcase VR to the world, which means both the public and other developers. Still, this doesn't really help us to focus that much. What is a VR game? It could be any genre or setting. And in the end, we decided to work on many different games to best explore what VR can do. As a result, we decided the main focus on tools and tech should be flexibility and speed, so we could be reactive to whatever concepts we thought were going to work best. We developed a brand new engine called LSSDK, which was fully multi-threaded and designed with the PS4 architecture in mind. To keep things flexible, we used a tiled forward renderer, and this allows us to add new shading models easily without having to worry about packing attributes into a G buffer, and also means transparencies can be handled identically to opaque objects. We also wanted to have the option of trying out stylized rendering and lighting models. We build a PC version alongside, which isn't optimized but allows us to have full WYSIWYG editing on PC. For my part, I implemented the direct lighting models for the new engine, based on the GGX lighting model, as well as shading models for pre-integrated skin, hair and eyes. We put a large effort into making a new game editor called Creator. Creator acts as an interface to the game engine, which is running alongside in a separate process. One nice thing about this is if the game crashes for any reason, Creator carries on running, so you can just reboot the game and carry on where you left off. You can hot reload any resource without restarting the game, so models, textures, animations and scripts can all update on the fly. This gives us a one-click export for most of our assets to seeing them in the headset. You can also have multiple tabs open running game sessions on different platforms. And this means you can have the game running in VR on PlayStation 4 while you're editing the game through another camera on PC. And this is Creator. Although it looks like the game is running within it, it's actually a display from another process. We also use a remote play functionality that's used for streaming to Vita to give you a display on PC while you're editing on PS4. We use Maya as our primary art authoring tool, though this is largely for asset creation, so models, skeletons and animations. The placement and gameplay functionality are done through Creator. We don't run our engine in Maya, but our shader system is available here, which means we can get a reasonably good idea of what an asset will look like in game. For the new engine, we decided that we'd have all our shaders go through materials, which is Sony Worldwide Studios' shared node-based material editor. Having a visual editor helps to increase the number of people who can author shaders. We write the lighting models in code and expose material parameters as an interface in a node graph. Personally speaking, I prefer writing code to node graphs a lot of the time for complex effects. Big node graphs can often end up being write-only, so you know what you're doing when you author it, and it all seems to make sense at the time, until you come back a week later and it just looks like spaghetti. We do alleviate this to a degree by creating custom nodes with shader code in. So all the not orange nodes in this graph are bespoke code with multiple inputs and outputs, and this really helps us to use the best fit of code versus nodes where it's suited. It takes us about a minute to generate a shader for PC and PS4, but we can iterate on them more quickly in Maya. As the Maya version of the shader uses a single permutation, it only takes us a couple of seconds to recompile. So now I'm going to talk how we applied the tools and tech to our experiences. So we've been developing on VR for 2 years now, working alongside the development of the headset and showcasing experiences at various shows and events throughout. The engine has also grown alongside in reaction to the team's needs. So I'm going to go through all of our experiences in order to show you how the engine has developed. So first I'm going to show you some footage of our experience which has the working title Into the Deep. It is still quite funny to hear screams coming from meeting rooms where people play that for the first time. We experimented with many different concepts, but the one we wanted to show first was Into the Deep. We showed this at GDC 2014 with the first public showing of Morpheus. The Deep is a trip through a coral reef in a diving cage down into the depths of the ocean, where you encounter an enormous great white shark up close. And we already had some pretty unique rendering requirements. We needed physically based scattering and absorption to give it a realistic ocean feel, caustics which diffuse as you go down further into the ocean, and we didn't even have a skybox, so we have to have a custom underwater surface shader to refract a cube map from above the water and reflect below the surface. But more than that, this was really the first test of our engine and tools. Basically everyone was getting up to speed at this point and learning how to use physically based materials. We didn't really have much time to rest though, because we swiftly moved on to our next game, which was VR Luge. VR Luge is an adrenaline-filled rush down a mountainside on a luge, dodging traffic controlled entirely through the headset through leaning. We showed this for the first time at E3 2014, so it was pretty soon after the last demo. For the luge we developed localized cube maps as we wanted to have reflections as you go through tunnels. We also added an atmospheric sky simulation to give a realistic sky colour and scattering on the scenery, which can be augmented with cloud textures. We had decal support at this stage. As we're using a forward renderer, decals can be quite expensive, so we tend to use stenciled alpha on decals where possible, but we do have the option of blended. And our prepass also outputs normals, which allows us normal blending. And the next game we developed was London Heist.
I'm gonna put some sweat in you little pieces. I don't give a monkey's what bank thinks about you. I don't trust you. And do you know why? Because there's only two people who could have taken Serena today. You or me. And went for me. Now you two where with her.
So, our first showing of the London Heist was last year at GDC, and it's an experience where you're being interrogated by a burly gangster called Mickey, who wants to know what happened during a botched heist. You then have a flashback to the heist itself, where you can interact with objects and have a shootout with dual move controllers. So we had a fair amount of time since the last game at this point, so there's many new features. The main one's a resolution increase. For the earlier demos we were targeting 1080p, but we moved up to 1.2 to 1.3 times that. That doesn't sound like a lot, but it's actually 1.7 times the number of pixels being displayed. And this was a huge challenge, so a large portion of our time went into delivering engine optimizations, which I won't go into detail on, but big ticket items are things like asynchronous compute light tiling and deferred shadows. We also added temporal anti-aliasing. I've previously seen advice about not using temporal AA on VR, and it is a trade-off. It does tend to have a blurring effect on the image, but we found that to create a sense of presence, it's more important to remove flickering pixels that make it obvious that you're looking at a game than it is to have a sharper image. It also takes a fair chunk out of our frame time compared with something like FXAA, and you have to be mindful of the artifacts which are more visible than VR, but we think overall the results are worth it. We showed reprojection for the first time as well. At this year's GDC, we showed a new version of PlayStation VR with an 120Hz refresh rate. Reprojection allows us to continue to render at 60 Hz, but rotates the rendered image based on the current headset orientation at 120. As well as smoothing out the motion, this process happens at the last possible instant before being sent to display, reducing latency. And this was a really big leap in presence. Removing the lag makes you think your head is moving within the environment rather than controlling a camera. And this was also our first use of the character shaders. And this is one area where it shows how unpredictable and varied the development experience was. We actually developed lighting models for skin, hair and eyes very early on, but they remained unused for a year. This was also our first attempt at interacting with a character in VR. We used Morpheme as our animation system, which lets us make Mickey reactive to your position and act differently depending on what you do, rather than being a linear narrative. The London Heist went down extremely well, and we showed another segment of it at E3 called The Getaway. So that brings us up to date. So on to exciting new stuff. So The Getaway was shown to the public at E3 last June. So what have we been working on since? Well, we have been working on some other experiences, but I can't talk about them just yet. After the Getaway, we had a pretty good core feature set and performance, so we started to work on some more cutting-edge techniques. So I'm going to talk to you about our new ambient lighting, some optimizations which allow us to hit high resolutions, and character shading improvements. We wanted to make some improvements to our ambient lighting system. The specular is okay and fairly industry standard using parallax corrected light maps, Q maps, sorry. But our diffuse ambient was captured at the same frequency, so we had a bounding box covering very large areas. And this gave a really flat look to the environment and didn't capture much variation in the bounce lighting. So early on in development we tried using light maps, but we abandoned those for a few reasons. We disliked the slow turnaround time of the bakes, and also having to lay out light map UVs. In addition to that, the first experience we made was a deep, and our light map solution didn't know anything about the scattering and absorption that are key to the look of that game. Light maps only also work for static geometry, so we still needed other solutions for dynamic objects. Our first thought was to simply generate more probes by flooding a scene based on the voxel representation of the level, but this would still take a reasonable amount of time to update. Bruno, one of our graphics programmers, had another idea and developed a solution called light fields. And this is a voxel-based global illumination solution that's fast enough to run in real time for VR. As well as giving us the flexibility to have dynamically updating ambient light, we also have the option of caching off the results. The benefit of this is instantaneous feedback while lighting. The solution also supports lighting from emissive meshes, which gives us some cheap area lighting where we need it. And so here's a Cornell box being lit entirely by emissive meshes. And this is the London High scene with our old lighting setup, which is largely real-time lights for the wall lights and a couple of ambient probes for diffuse and specular. And this is the light fields version. You can immediately see a lot more variation and depth into the ambient lighting and more correct wide-scale occlusion. So light fields is a good fit for VR. As well as the speed, it's a world-space solution, so there's no difference between the eyes. It's stable, so there's no flickering or shimmering, and it's resolution independent in that most of the work is done off screen. So on the left here there's a shot with light fields, and on the right is a shot without. You probably can't really notice much of an improvement, and that's deliberate, as this was a test to show how we can reduce our light complexity. The original version used a lot of manually placed fill lights to create interest in the ambient. On the right you can see the amount of complex lighting we have in the scene to simulate it. With light fields we can massively simplify this down to a few key lights, while still maintaining the look. You do lose some artistic control, but interestingly the original version done by eye was remarkably similar to the light fields version. And you do still have the option of placing fill lights into the scene as well, and we can set these to only affect the light field, making them essentially free. The big win with light fields has been the speed of iteration, and also giving us much more interesting lighting results without having to manually place fill lights. We're currently using a static version of light fields in London Heist, and we need to work on a large-scale version for VR Illusion Into the Deep. The main disadvantage compared to light maps is it's much lower resolution, and this means you can only really use it for ambient or fill rather than baking spotlights onto the environment, for instance. So next I'm going to talk about how we manage the resolution requirements for VR. So the left image shows what we rendered before distortion for the lenses. The red area isn't needed, so we mask it out. This saves us about 20% frame time for no visual loss. I think this is pretty much covered in all VR SDKs at this point. But the lens distortion applied for viewing in a headset means that we have to render a higher resolution in the center of the image. Ideally this should be 1.4 times 1080p to get 1-to-1 pixel matching, and I'm going to show you a little video to explain. So here you can see the final image we need for the lens and the headset. So we need to render a larger image and then essentially shrink wrap it onto the final image. And if you notice, the center remains at the same size. As you can see, there's a lot of resolution used on the outside of the image. Not only is it oversampled compared to the middle, but generally speaking you don't really care about it as much. Other solutions that have been proposed in the past include rendering a high resolution insert in the center, or NVIDIA's solution, which is to have 9 render targets stitched together. But we wanted to have a solution that didn't increase the number of targets, because doing so has a number of disadvantages like extra vertex processing, having to render overlaps to have a smooth transition between different resolutions, and the extra CPU burden of having to render the objects multiple times. So we came up with a technique which we call a resolution gradient. So here's a shot of Into the Deep. And we mask out a dither pattern in increasing amounts, so 25%, 50%, and then 75% of the pixels are discarded at the edges. We currently mask out 2x2 pixel quads, as masking out single pixels isn't GPU friendly, but I'll come on to this later. And we change these dither patterns every frame. So we then fill these holes by taking neighbouring values through a dilation filter. And this does give us some nasty stair-stepping artifacts, as you can see on the vertical lines here. But our temporal anti-aliasing can clean most of this up, as we're constantly feeding in new information due to the varying dither pattern. So this technique isn't perfect. You do get some quality loss, but you're generally pretty forgiving if it isn't in the centre of your field of view. And we save about 25% GPU time, so it's a pretty good trade-off overall. We're working on a technique using hardware anti-aliasing to only mask out single pixels rather than 2x2 quads. And we're hoping that this should improve the quality to the point where you won't notice it. Okay, so the last batch of new techniques I want to talk about are for character rendering. Characters are really important for the London heist. They're very close to you, and they have your full attention. It's important we get the shading right so that you can read the facial expressions clearly. So the first thing we added was vertex renormalization. This is a process we do in a geometry shader, and it calculates new face normals based on the deformed mesh. We first identified this as an issue on iPet on PS3, and we had an SPU's process there to recalculate the normals dynamically. Maya always processes meshes in this way, so animators need this to work the same in-game if they want their facial expressions to match. If you rotate joints, the normals work pretty well. They just rotate with the joint based on the weighting. But facial animation largely uses translations rather than rotations, and that doesn't update the normal at all. The left section of this image shows what happens if you translate a joint on a skin mesh using a standard game pipeline. And the normals all continue pointing upwards, so the lighting's flat. The right-hand section is what happens when you generate new face normals. Everything works like you'd expect. So here's a standard game skinning pipeline. And this is the same mesh with recalculated normals. Now, it's difficult to say that one looks more correct than the other from a still, but the important thing is that normals are constantly changing on the recalculated version, making the face feel much more alive. So the next thing we added was support on the skin shader for bent normals. Bent normals are a normal map that store the average unoccluded direction of a point on the mesh. When you apply them to your ambient lighting lookups, you can reduce the amount of light leaking coming through areas that should be occluded. With storing bent normals and wrinkle maps, we ended up having quite a lot of textures. To reduce the memory and bandwidth requirements, we stored the wrinkle maps and bent normals as offsets from the high-resolution base normal map. We only need these offset maps to reflect coarse lighting changes on the face, with high-frequency detail like pores and smaller wrinkles remaining on the base map. We packed these 5 offsets into 3 textures using BC7. So this is standard normal mapping, and this is with bent normals. And you can hopefully see the reduced light leaking, particularly on the bottom of the nose. So lastly, I want to talk about our ambient occlusion on characters. We had a pretty good refractive eye shader, but the most common complaint about it is it didn't seem bedded in enough. We had similar complaints about teeth being too bright. Now this really comes down to having a good AO solution, and in this case screen space occlusion didn't really give us the resolution or control we need. Previous solutions to this problem have included skinning geometry with an AO gradient onto the eyelids and lips, but this is pretty fiddly as it's difficult to manage the interpenetration on the meshes with all the poses. So I had the idea to generate a distance field representing the eyelids and mouth. Looking at the skeleton, we already had joints fairly well placed in these areas, so I just create a ring of line segments using these positions and calculate the distance to the nearest one. And then we can then use this to generate AO and cavity values. So here is our eye shader, and here's the eyelid joints. This shape represents a distance field from the line segments joined between those joints. And we can get to this in the shader as well. But better still, as the eye is roughly spherical, we can project these joint positions onto the eyeball surface reasonably easily to get a better result. And this is the field applied to the eye, exaggerated a bit for clarity. There are artist control values to adjust the amount and distance of AO and cavity values independently. So as you can see, it's a pretty large difference. And this is a shader code. So thanks to Inigo Quiles for the distance function. It is a fair amount of maths, but the pixel coverage is generally low. This is an example of one of our bespoke shading nodes I mentioned earlier. I think that this is much more readable in code than it would be in a node graph. So here's the face without distance field AO, and with. So the facial expression here reads quite differently with the AO applied. We also apply it to the teeth in a similar fashion, but without the spherical projection. So my last section today is on optimization. So we obviously have to be really conscious about performance. 60 frames per second in a 2D game is difficult. 60 frames per second with no frame drops ever, greater than 1080p resolutions, is even more difficult. On top of that, after tracking and reprojection are taken off, we have about 15 milliseconds budget on GPU. And it's really important to keep a constant 60 frames per second, as immersion is greatly improved, and low frame rates can cause nausea. And it's worth the effort too. VR may mean that you have to make assets that don't look as refined as in a 2D game, but the VR experience is transformative. But still, as game developers and artists, we always want to push things as far as we can. There's nothing really special about optimization for VR, other than that things need to have more detail if you can get close to them or pick them up, but performance needs to drop to appropriate LODs quickly. As a result, we spent a lot of time on our LOD tools. We use Simplygon as our primary tool for generating them. We found that adding the functionality to generate mesh LODs, which are basically a poly-reduced model using the same materials, was very easy to get in. The proxy LODs are more difficult though. Proxy LODs can bake a mesh or number of meshes with many different materials into one entirely new mesh in textures through a voxelization process. The mesh can in many cases be more efficient, particularly for the low LODs, as it doesn't have to respect the existing UV layout. Because it bakes a new normal map, the mesh often lights more correctly also. The main disadvantage is that you generate new textures for each LOD, so your texture memory requirements go up, but we have some strategies for dealing with this, as I'll go into shortly. The problem with implementing proxy LODs is that Simplygon needs to understand how your shaders work. We have a wide variety of shaders that we want to bake down, and although Simplygon has functionality for this, we didn't want to build a system to translate our shaders over. But Andrew Maximov from Naughty Dog had a cool suggestion. If you can already render your materials in Maya, and we can, just flatten them into UV space and do some renders. So that's what we did. So here we have a drone from the deep. It's a relatively simple shading setup of just 2 materials and 7 textures. Obviously with layered shaders you can have a lot more inputs. The input mesh here is about 14,000 polys. So the first thing we do is to bake all the material outputs from the shader. And these correspond with the values that we pass from our material editor into our lighting models. So this is a shader that's used on a drone. As you can see, it's pretty simple. It doesn't really do much other than read a few textures and pass some values along. So we've run the model through Maya's automatic UV mapping to generate a new set of unique UVs, and use the vertex shader to flatten the model into UV space. So here's the process of world space normals. And we go through this process for 6 maps, which are base color, world space normals, metallic, gloss and occlusion packed into one texture. We render out emissive, but that's an HDR value, so we pack this into RGBD format over 2 textures, and opacity. We also pad the edges to remove any seams. And this all gets sent into Simplygon, and we end up with our LED1 model, which is about 3,800 triangles. So the textures you can see here don't make a lot of visual sense, as they've been swizzled. We convert the base color from RGB into YCOCG, Luma and Chroma format, and store these textures at different resolutions. So the largest texture here contains the normal X and Y, the gloss, and the base color luminance. And these are the most important components. The next texture contains the base color's 2 chroma channels, metallic and occlusion. And this can not only be stored at a low resolution to save memory, but we also bias the texture sampling to always sample 1 bit lower than usual to reduce texture bandwidth. The last texture contains the emissive stored in RGB pack format. For this model we need emissive, but obviously not all models do. So emissive and opacity textures are only generated and used on models that need them. And all the textures are compressed as BC7. So we already store the second texture at a low resolution, but in many cases even that can be improved upon. So here we've replaced the second LOD texture with just vertex colors. There's a noticeable difference on this model, particularly on the bottom of the turbines. But many models have very little variance in their chroma or metallic parameters, and you can only really spot a difference in the occlusion. And the result of this is that many of our proxy LODs can represent the full physically based material using only 1 texture read. And I'm hoping on our next project that we can get some of these packing techniques onto our main models, as well as the LODs, to reduce our texture bandwidth. So I think that's about all I have time for today. So in conclusion, we had a lot to do at the same time. The arrival of PS4, developing a new engine, and also writing the rulebook for VR as we went along was really hard. Our approach to making a flexible pipeline made this a lot easier. If in the future we develop a title which has more known content, it's likely we'll shift our focus away from the pure flexibility we have now to solutions that are a bit more bespoke for the game. However, we're likely to keep many of the same philosophies in the future, particularly around keeping the iteration times down to as short as possible. So thank you for coming, everyone. I think possibly got time for a couple of questions, maybe? Not very well. Okay.
Oh, hi. Thanks for your talk. I was wondering, you mentioned that you were moving to forward renderers. I was wondering if you're final with that decision, and, well, a lot of people in VR know why, but if you can elaborate why it's important for you to do forward rendering.
So the main reason we decided to go for a forward renderer to begin with was really just to keep the flexibility open. So we wanted to be able to put in lots of different light models and to be able to do stylized rendering. I think it's turned out to be a smart decision in that the bandwidth requirements for forward are much lower than deferred as well, so I think it scales quite well to having the higher resolutions for VR. Having said that, we haven't actually tried a deferred renderer against it, so I don't know whether it's the best solution. We probably need to do some more work to evaluate against a deferred solution in the future. The thing is, I mean, forward and deferred aren't as different as they used to be anyway. Now that we use tiled approaches on both, the only difference really is, like, do you store your material inputs in a texture or do you just pass them straight into material? So they're not so different. We could probably switch over to a deferred renderer if we need to.
I was just kind of curious, why do you guys still do a tiled approach when you're doing forward rendering? Because with the deferred approach, you obviously need to tile it because of the size of your G buffer, but
yeah.
If you're doing forward rendering, I assume you're just outputting the actual final color values, so...
It's basically so we can support many lights. So we do a light tiling pass to work out where the lights are in screen space and then build up an index list of all the lights in that particular tile, so that in the shader loop you can just basically loop for all the lights that are in that tile, so you can support essentially an infinite number of lights. So as opposed to the previous forward approaches, it's basically just for the number of lights is the short answer. So.
Thank you.
Okay. Thank you very much. If anybody else